So today's lesson is going to be slightly longer than previous ones, and there's not going to be an exercise after it. So what your task for today is to thoroughly watch this lesson and to make notes from it. Because even though the main topic is bearings, you can see then the learning objectives, to be able to understand the concept of bearings, measure bearings, and complete calculations involving bearings. That requires us to understand a few other topics. Now, we've done those other topics before, but we still need to have a reminder of them now. So you might need to pause the video a few times. You might need to rewind it. But what I'm expecting to see from you today is a photograph of some of your notes from this. Okay, so let's imagine we know nothing about bearings, and we've got this challenge in front of us. Can you pop the ball? So there's a ball there, and we've got to try to get the ball in the pocket. Okay, and we've got something down here. It says bearing. Now there's a little angle symbol there, so we can guess that it's angles. We've got some tools over here. So if I get the protractor and I move it here, then it looks to be, well, about 120, maybe 122 is going into the center of the pocket. So let's try that. Okay, and we'll just see if it does what we expect it to do. So I'll click go, but it doesn't. Okay, 122 on my protractor was pointing up there, but it went down here. So something's gone a bit funny. So what if I reset that? And instead of trying to get it straight in the pocket, let's do a little bit of investigation work about what a bearing could mean. Let's start off with 0, 0, 0 and see where the start of the protractor should be, because I started off with the protractor in this default position with 0 over here. But if I let the bearing go on 0, 0, 0, we'll see where the protractor should start, because it clearly shouldn't start there. Okay, so 0 is going straight up, which means if I get my protractor and I rotate it so that 0 is straight up, now this protractor should be in the same sort of positions as bearings. So if I now, let's make it bigger so I can see what's what. So starting with 0 up there, I'm going to want about 49, let's say. So let's shrink this down again. Let's go. So I don't want anything in that first number, and let's make that 19 and see if we get it right. Straight in. Great. Okay, so that little bit of investigation work there teaches us a little bit about bearings. Okay, so let's get ready to make a few notes on that and formalize all this. So bearings is a sort of compass direction. You might have heard the phrase to gather your bearings, to get your bearings, is to sort of understand sort of the place around you, know what sort of direction you're pointing in, that sort of thing. And as we saw on that snooker table, 0, 0, 0 was north. So bearings start from north. A compass will always point north, because that's where bearings start. And then as we go around, the angle changes, and so the bearing changes. But the few rules are that they're measured from north clockwise. So this is 90 degrees round to east, but we're not going to say that this is 90 degrees around to west. We would say that it's 270 degrees around to west, because we're always going to go clockwise. And bearings always have 3 digits. You saw in that snooker table thing, there were 3 digits, 3 spaces for my digits, and they always should, which means that if you only want to go 90 degrees, you would put in 0, 90. I'll explain why a little bit later with a different sort of real life example. Okay, so north is 0, 0, 0. Northeast is 0, 4, 5. East is 0, 90. 1, 3, 5. We don't need the leading 0 now, because we've already got 3 digits in our angle, and it carries on around. And there's no 360 degrees bearing because that is back to 0, 0, 0. Your bearings are only going to go between 0 and up to 360. We're not including it, so 359.999, whatever. Okay, so that's some basics of bearings right there. And then we've kind of got the first bit done now, understand the concept of bearings, but we've got to be able to measure bearings and complete calculations involving bearings. So we're going to have a look a little bit at that now. So measuring bearings. You might be asked to measure the bearing of B from A. And even if everything on the previous slide seemed to make sense, you just might get confused by this because looking at the diagram and looking at what you're going to be asked to do, it's a bit tricky. So let's just think about what the wording of this says. Measure the bearing of B from A. So from A, that's our starting point. Our starting point is A. And we've got to remember that bearings are measured from north. So that's going to be our first step. So draw a north line at the start of the journey. And that means you could get your protractor and you can line it up so the 0 is pointing north. And you can measure the angle we've got now. So measure the angle clockwise from the north line to the journey line. And the way to imagine what you've got to do here is imagine you are standing at A and you are looking north. What the question is asking you to do is how many degrees would I have to turn so that I'm now facing B? Because that's the whole point of bearings, is to get yourself pointing in the right direction so you can travel somewhere. So you're currently at A, you get your compass out, and your compass is pointing automatically north, so you know what way that is. And then as you turn to point face B, you can see what bearing it is. And remember 065 because bearings have to have 3 digits. Okay. The questions are always worded like this: measure the bearing of B from A. It might make more sense if we said from A to B, but it doesn't get worded like that for whatever reason. In all questions, they have it worded like this, so we've got to get used to it. From A, it's starting at A. Okay, so next one. You could be asked to draw bearings. So we could be asked to draw bearing of 100 degrees from the point A. So same first step as before. Imagine you're standing on A and we want to know which direction north is. So we want to draw a north line from the start of the journey. And it's going north. And then we're going to get our protractor. You're going to put it so that the center cross is there. 0 is pointing up here, and you're going to go 100 degrees on your protractor, make a little point, and then draw a line going through that, and there's your bearing that you've been asked to draw. It's always important to go clockwise. Okay, let's have a look at something else. So you could have to calculate bearings. Now, when it's asking you to calculate rather than measure or draw, it's not get a protractor out and measure it. It's use angle rules to calculate it. And this is one of those other topics that I said is related to this, which we need to know. And so the bearing of A from B. So from B, we're starting at B. There's my north line. I want to turn until I'm facing A. What's that angle? So it's asking me what this angle is here. And I've got that 46. I know that the angles on a straight line add up to 180, which means that missing angle, the bearing I'm looking for, is 134. But I needed to know that rule. If I got a protractor and measured it, probably wouldn't say 134. It'd probably say something different. So let's recap some of the angle rules which might be useful. So the angles on a straight line add up to 180. We've just seen that. Angles in a full turn add up to 360. So you can imagine a question where you've been given a certain angle and the bearing's the missing one from a full turn, and we've got to work out that. And these parallel line rules are also useful because if you think about a diagram with a few different points on it, if they all have north lines on them, those north lines are pointing in the same direction, they're parallel, which means some of these rules might apply, which means you've got to know your corresponding angles rule, your alternate angles rule. So these are parallel lines here. So this makes the F shape, and it means that these two angles are the same. The F shape could be upside down, backwards, or sideways. Same for the Z shape. The angles inside the Z are the same when these are parallel lines, and Z could be upside down, sideways, or backwards. Then we've got one here which is slightly different. We've got interior angles. So you've got your two parallel lines here. The two angles inside add up to 180. So that could be a C shape, it could be a backward C, it could be upside down looking like a U or an N. So just the angles within the two parallel lines add up to 180. And this is slightly different again. It's vertically opposite angles are equal. So when you've got an X, and it's got to be a proper X where this is a straight line, not where it goes up to here and then changes direction slightly. But if that's the case, these two angles are the same, and these two angles up and down are the same. So you look for the X shape. Okay, so if we know those angle rules, it's going to help us calculate certain bearings. But we've still got to remember the important things, which is that bearings start from north, go clockwise, and have 3 digits. Okay. Another thing we need to know is, because I've been talking so much about using this to find your directions, sometimes a map might tell you what bearing to go on and also how far to go. And the map you'd be using would have a scale. The map would not be going life size, because if you do that, then a map of London would be the size of London. It would be ridiculous. So you've got to use some scale, and you've got to know these conversions to understand the scale properly. So 1 kilometer equals some amount of meters, 1 meter equals some amount of centimeters, and 1 centimeter equals some amount of millimeters. Now, hopefully you know these answers. Hopefully you've already sort of said them out loud or written them down. But if you didn't, I'll talk you through them now. So 1 kilometer is 1,000 meters. And the way to remember that is the prefix kilo means 1,000. So there's 1,000 meters in a kilometer. There's 1,000 grams in a kilogram. There's 1,000 amps in a kiloamp. Any unit you want, if you put a K in front of it, it means 1,000 times bigger. 1 meter is 100 centimeters. Now, I'm sure you all know that, but the reason you could remember it or apply it to other things is because the word centi means 100th. So a centimeter is 100th of a meter. Think about the word century, and that represents 100 years, and so it's the same here. And 1 centimeter, well, hopefully you all know that's 10 millimeters. Probably just remember it from on a ruler. The prefix milli means 1,000th. And you might think, well, why is the answer 10? It's because it's 1,000th of the original thing, which is a meter. So you got to go 10 times bigger to get to centimeters, and then another 100 times bigger to get up to meters, so it's 1,000 altogether. So the answers for these blanks are 1,000, 100, and 10. And the good thing about the metric system is it's always going to be stuff like that. It's going to be thousands, hundreds, tens. It's not going to be 37.4. Okay, the imperial system, feet and inches, stones and pounds, and things like that is a little bit harder to work with, and we're sort of moving away from it gradually. Okay, so let's look at some unit conversions. So we've got our reminders up here. And if you want to turn kilometers into meters, you have to times by 1,000. If you want to turn meters into centimeters, you've got to times by 100, and so on and so on. And if you want to go the other way around, you're going to be dividing. And the way to get this the right way around, because you might think, well, kilometer going to meters are smaller, so should I times or divide? You might think smaller means I should divide. You just got to think, am I expecting to have more or less as my answer? Because if your answer's at the moment in kilometers and you want to turn it into meters, you should have more meters, which means you're going to be timesing. Or you can just remember these different things I haven't written down and refer back to them until you remember them. So let's look at some questions. Okay, so you're going to need a calculator for these questions. Let me just grab a calculator. And you're going to you're going to want to look carefully at the scale and what we've got here, and just appropriately turn it into it. So the first one there in red says we've got a scale of 1 to 50,000, and we want to know how many kilometers are going to be 8 centimeters on the map. So if we use that scale straight away, then 8 centimeters on the map, that scale means, is going to be 50,000 times bigger in real life. So 8 times 50,000 using your calculator is 400,000. Okay, so in real life, that is 400,000 centimeters. But that's not really a useful thing. We want to know it in kilometers. So we've got to turn centimeters into kilometers. So if we have a look over here, we can't go directly from centimeters to kilometers, but we can go from centimeters to meters, and then meters to kilometers. So we've got to divide by 100 to turn it into meters. So 400,000 centimeters is 4,000 meters. And then if we divide by 1,000 to get to kilometers, we will get that is 4 kilometers in real life. Okay, so 1 to 50,000 scale. Kilometers is represented by 8 centimeters on the map. The answer is 4. Okay, so we'll look at the yellow problem next. So we've got a scale of 1 to 25,000. How many kilometers are represented by 4 centimeters on the map? So again, let's use the map scale to figure out how big this is in real life. So 4 centimeters on the map times by 25,000 is 100,000 centimeters in real life. So we've got to now turn the centimeters into kilometers. So centimeters to meters, let's divide by 100. That's 1,000. And meters to kilometers, divide by 1,000, which means it is going to be 1 kilometer in real life. Okay, then using scale of 1 to 100,000, how many centimeters on a map would represent 12 kilometers? So we're doing it the other way round now. Okay, so we've got the real life scale and we want to turn it into the map. So we're going to just do it, everything we've just been doing, but just backwards. We're going to turn the 12 kilometers into centimeters, and then we're going to divide by the map scale. We've previously been timesing by the map scale and then turning the centimeters into kilometers, and do it the other way around. So kilometers to centimeters, I've got to first times by 1,000 and then times by 100. So 12 times by 1,000 is 12,000, times by 100 is 1.2 million. So 1,200,000 centimeters. Then if I divide by that map scale, so divide by 100,000, I'm going to get that it is 12 centimeters on the map as well. Okay. Don't just be fooled by thinking, oh, it's going to be whatever this number is in kilometers, it's going to be centimeters. You saw on the other ones it wasn't. It just happens to be on this one that the map scale and the conversion rates cancel each other out, but it's not always going to be 12 to 12 because this wasn't 8 to 8, this was 8 to 4. It's not always going to be like that. This wasn't 4 to 4, it's 4 to 1. So let's do one more, the last one, the blue one there. So we've got a scale of 1 to 25,000. We want 5 kilometers. We want to know how many centimeters that is in a map. So first thing we've got to do is change the 5 kilometers into centimeters. So first, let's change it to meters. So 5 times 1,000 is going to be 5,000 meters. And then change it to centimeters by timesing by 100. And that's going to be 500,000 centimeters. So 5 kilometers is the same as 500,000 centimeters. And then we will divide by our map scale. So divide by 25,000. And we'll get that as 20 centimeters on the map. Okay, so using the map scales might be handy when it comes to bearings. Okay, Hopefully that made sense. Hopefully, if it didn't, you might want to go back and have a go at sort of, as I say, the calculations, writing them down, and seeing what they look like, and seeing if that makes a bit more sense. But otherwise, let's move on. So, you might be asked a bigger question like this. It says it's on scale drawings and bearings, so it's going to involve the angles and the lengths, and putting everything we've got together. So we've got a speedboat leaves the harbour on a bearing of 060 and travels 8 nautical miles. Then travels on a bearing of 150 for a further 6 nautical miles. Draw a scale drawing to show the voyage, measure the distance and the bearing of the speedboat from the harbour. So we've got a situation where we've got a scale of 1 mile to 1 centimetre. That's nice and easy. So we don't need to go through the lengthy process we've just been through. Our scale there is such that this 8 nautical miles is going to be 8 centimetres. This 6 nautical miles is going to be 6 centimetres. That's handy. So this is the steps of how this question should work, and I'd be interested to see sort of when you follow these steps what it looks like, because this is the sort of the main part I'll be looking at when you submit your work. Okay, so try to make sure that this diagram is clear. So you put an X on the left hand side of your page about halfway down. The reason I say that is so that you've got space, because if you start top left, then there's no space for a north line and there's no space to draw your journey. I'm telling you that if you put your X on the left hand side of the page about halfway down, that'll give you plenty of space you need for where this journey is going to take you. So then you draw a north line. So from your X, you draw a line straight up and put a little N on the top of it. Then we're going to measure a bearing of 060 and mark it with a dot. So that is when you get your protractor and you put the cross on the X, have it pointing straight up, put a little mark where 60 is, like we did in the previous examples. Draw a line through it, but make sure this line is 8 centimetres, because that means they've gone in the right direction for 8 nautical miles. Then draw a north line from this new point, because now from this point we're going to go on a different leg of our journey. So from this new point, 8 centimetres along, we're going to draw a new north line. And then we're going to do the same thing, but we're going to draw a bearing of 150 this time. So your protractor is going to go on the new cross. And then you're going to have 0 pointing up to north. You're going to measure around to 150, mark it with a dot, a 6 centimetre line, because now we're going 6 nautical miles. And that's the journey it went on. But that's part A answered. And then we've got to measure the distance and bearing of the speedboat from the harbour. So the speedboat that started at the harbour and it's moved along to this new place, if you join up the end point to the start point, then that'll be able to answer how far it is from the harbour. Measure the distance of the line, and that'll tell you in nautical miles how far away it is from the harbour if you measure it in centimetres. And if you measure the bearing, so if you draw a new north line at this new point and measure the bearing around, remember clockwise, starting from north, 3 digits, and that'll be the bearing and distance from the speedboat from the harbour. Okay, so have a go at that. Take your time, do it accurately, and I'll say this is going to be the most difficult part of the lesson, because this is examples putting everything we've done together. Okay. One more thing I want to talk about is some real life bearings, because a lot of maths, it's difficult to see where it's used in real life. It can seem quite abstract, even though it is useful in everyday real life. It's not sort of apparent, but this is sort of more of an apparent thing that you can sort of get to grips with. You've got a map here, and you can imagine if you were in a plane and you wanted to go from one place to another. When you're up in the sky with the clouds, there's no sort of landmarks. You're not following a road. You have got to follow sort of certain instruments in the plane, and one of them is going to be telling you what angle you're flying at, what bearing you're flying at. So it's important to understand these so that you can navigate to your way up here. And if you're also at sea, so if you're at sea up here, it's the same thing. If you get far out to sea, you can't see landmarks. You can't just sail towards something. You've got to be able to measure the instruments, follow the map, and go in the right direction for the right amount of time or for the right distance. Okay, so that's why it's used in real life. And that's why you should also think about it as I am standing here pointing north, and which way do I want to, how far do I need to turn in order to get to where I want to go. And the reason that it's got 3 digits always is because in sort of the old days when sort of there was radio communication, sometimes the reception wasn't that great and you couldn't quite hear everything. And so if there was a bearing of 94, perhaps you missed the first digit and it was actually 194, and that's a big mistake. So to counteract that, what they had to say was 094, and you wouldn't proceed until you had heard all 3 digits, and that way you knew you hadn't missed anything. Okay, so that's why it's got 3 digits. This is why compasses point north. This is why this is useful in real life. So, like I said, make notes, have a go at doing that scale drawing, photograph it, upload it to me, and no exercise today, but we will be using this information to answer exercises in later weeks. Okay? All right, that's everything for today.